in the Distributed Systems and Security Group at Microsoft Research Redmond. His research interests lie in the areas of systems and network security. He received his PhD in electrical engineering and computer science in 2006 and his master's degree in computer science in 2003, both from UC Berkeley. And he received his master ME in 2000 and BE in 1998 in electronic engineering from Tsinghua University in China.
Thank you very much, Dong Yan. Thank you very much for inviting me here. It's my first time to Middle West. I really enjoy my visit. And today I'll be talking about automatic signature generation for unknown vulnerabilities. It's a joint work with my colleagues Marcus Peinado and Helen Wang. Carl Chen and Michael Lacasto was involved in this work when they did their internships. So zero-day attacks that exploit unknown vulnerabilities is a big problem because zero-day attack means there's no patch or signature available to detect them or to filter them out. Symantec found there are 20 unknown vulnerabilities exploited between July 2005 and June 2007. So it's a serious problem, and however, current practice in new vulnerability analysis and protection generation is mostly done manually. So the attack is out there, but we need to take a lot of time to manually analyze them. It's really not a good idea. So our goal in this work is to automate the process of protection generation for unknown vulnerabilities. So nowadays, how can we protect a vulnerable application? The common way is this software patch. So we patch the binary of the vulnerable applications. And the other way is use this input filter. You can think about input filter as either like a network firewall or module sits on the I/O path. And a data patch, we call data patch, is basically we patch the input instead of binary. The advantage of data patch comparing with software patch is for software patch it's hard to roll back and takes a lot of time to do, and it's time consuming. For data patch, we can roll out a quick data patch. If things changed or doesn't work very well, we can easily just take away because it's just a filter. So our work is focused on automatic data patch generation. Here, let me give you an example of what we mean about data patch. This is a data format specification. So here, specify the SQL message. The SQL message for the slammer attack is basically have a first byte as a type and followed by a buffer, a sequence of bytes. Then there's a state machine, and state machine for SQL attack is quite simple. This is for the SQL protocol here. And here's a handler. And the data patch is basically a vulnerability predicate on the input fields. Here we can see that the data patch says if the first byte, the type equals to value 4, and the size of the rest of the message is greater than 97, then this is an exploit. So what we are looking for is this vulnerability predicate on the input fields. So to solve this problem, we developed a system called the ShieldGen. The goal of ShieldGen is to automatically generate a data patch for unknown vulnerability, given an attack instance and its format. The basic idea of ShieldGen is the following. So we construct new potential attack instances, we call them probes, based on the initial attack instance and the format. Then we feed this constructed attack instance to a zero-day detector, to an oracle, to decide if this new instance will trigger the attack or not. We do this back and forth so that we can figure out what matters, what doesn't matter in the original attack, which give us the vulnerability predicate on the input fields. So here's a system overview of ShieldGen. ShieldGen has 3 components. The first component is a zero-day attack detector. The system works the following. Assuming the zero-day attack detector monitors suspicious traffic, then when the zero-day attack detector detects there's a zero-day attack, it will send the zero-day attacker to this data analyzer. Based on the data format, the data analyzer will parse the zero-day attack and to generate the semantics, all the fields, all the sequences of the attack data, and parse it to this probe generator and analyzer. The probe generator and the analyzer will construct new attack instances based on the semantics and the original attack instance to construct the probes. Send it to the zero-day attack detector. The zero-day attack detector will say, oh, this probe successful, means exploit the vulnerability or not. We do this back and forth based on the previous probes until we can generate a data patch. So for the zero-day attack detector, actually anything that can detect attack can be used here. But in the actually, before I talk about zero-day attack detector, let me give you a background on this dynamic data flow analysis. So dynamic data flow analysis, the basic idea is to track the propagation and operation on input data. Assuming here we have the chunk of memory, and we track the syscalls of the input function, for example, like a read file or receive a network message. When we read the input, we'll mark the buffer that stores the input as tainted. We also track the taint propagation, so when the memory is copied to another part of the memory, we mark the destination buffer also as tainted. The dynamic data flow analysis allows us to understand how the input data is being processed. So I want to introduce dynamic data flow analysis because the zero-day attack detector and the following work about the Tupni both used this technique. So in the Shiogen system, for the zero-day attack detector, we use a system called the Vigilante. Actually, Shiogen is not limited to use Vigilante. Anything that can be used to detect attack can be used here because it's just an oracle. And some Vigilante use the dynamic data flow analysis. It basically check three conditions. For example, it will check if the input is ever being used to overwrite the return address, or the input data is being executed, or the input data used as an important argument to syscalls. So Vigilante also can identify the offsets of the offending byte, which we will use later on for our vulnerability signature generation. The second part of Shiogen is this data analyzer. What is in Shiogen, we use a GAPA. It's a generic application level protocol analyzer. What GAPA does is GAPA has a generic runtime. Given the protocol spec and given the network traffic, GAPA will parse the network traffic and provide the protocol context. For example, which protocol state you are currently at, what are the message, the fields in the messages. And also GAPA can be used for file format specification and analysis. So the question is this: GAPA requires all kinds of data analyzer. They require this protocol spec. The question is, what if when we see a zero-day attack and the data format, the format spec is not available or takes a long time to derive? Our solution is to combine Shiogen with a new system called Tupni. Tupni will replace this data analyzer, and we don't require the data format anymore. We just require the vulnerable program. It's always there. And what the Tupni does is Tupni can, based on the vulnerable program, Tupni can parse the zero-day attack and generate attack data with semantics. With Shiogen and Tupni, we can automate this complete loop. Basically, here shows that once we receive a suspicious traffic, everything is automated, and at the end, we can derive the data patch. So in the following of my talk, I just give the motivation and the overview. In the following of my talk, I will first talk about Tupni, is how to reverse engineering the input format. Then I will explain how Shiogen to generate the probes and analyze them. At the end, I will conclude. So the goal of Tupni is to automatically reverse engineering the format of network of file inputs given a parsing program. And Tupni is not only can be used for like a vulnerability signature generation. It can also be used for like a fast testing. If you don't know about fast testing, the basic idea of fast testing is to construct random or manipulated inputs, feed it to program, and see if the program will fail or cause any access violation. And to generate inputs, people usually require the input format so that we don't waste time on those invalid inputs. The key intuition behind Tupni is how a program parses and processes input reveals rich information about the format. And so based on this intuition, our approach is use dynamic data flow analysis, as I explained earlier. So we are not, there has been a bunch of work that trying to solve the problem for reverse engineering the input format. It starts from like a network trace based. It's basically like a product informatics and discoverer. They look at the network trace. And another line of research is using dynamic data flow analysis, like work from here, auto format and Zhiqiang and they did this FSE paper. So it's a lot of related work here. And but all of this work basically focused on field identification. And in Tupni, our main contribution is we try to identify record sequences. What is a record sequences here is record sequence is arbitrary sequences of aggregated data elements. For example, here I show example is this HTTP request header fields. So each one saying this is a sequence of this 4 records. And actually these 4 records, according to HTTP protocol, they can be in any arbitrary order. And the problem is if we don't understand record sequences, here we will derive 24 format because it's a enumeration of all the possible orders for these 4 records. And this redundant format basically may cause a lot of problem because what if it's a large number? So other contributions of Tupni is we identify record types. The intuition is a sequence of records are usually constructed from a small set of distinct types, and we want to identify what they are. And third thing is we identify constraints. So for input message, particularly for applications like fast testing, or we want to construct valid inputs, we need to know the input constraints. Such as this is a length field, specify the size of a record sequence. This is a checksum that checks of the header. So we want to fix them out. And the last thing is the format aggregation. So dynamic analysis has a generic inherent limitation that you only see the execution path you analyze. You have a limited view into the program. Then the result is if you only look at one input instance, you get an incomplete format. And we try to mitigate this problem by generalize the format over multiple inputs in Tupni. So let me first give you an overview of how Tupni works, and then we'll talk about each component. So the input to Tupni is a bunch inputs of network messages or files, and also the application binary. We don't require the source code. Then we collect the execution traces of the binary parsing each input. For the execution traces, you can think about it as a sequence of x86 instructions. That's just an execution trace. Then we work on the execution trace. First, we identify fields. Then we identify record sequences. After that, we analyze record types. Also, we generate constraints based on the execution sequence. At the end, we aggregate the format and derive a format for the input. So I will talk about each component one by one. So in my presentation, I will use this simple running example. This running example basically is a toy program parser input. The input, the first field specify the number of records in this input. And follow them, each record starting with two fields. The first one specifies the type of the record. The second one specifies the size of the record. Then in the parsing program, we have a loop. We read in each record, and we use a record handler to handle them. This will be my running example. To identify fields, the basic idea is x86 instruction operands imply input chunks. Here's a simple example. Say we move the first 4 bytes of the input to a buffer, and we compare the buffer with certain value. What this tells us is these 4 bytes are likely to be a field. And the problem is this basic idea works in general, but there are problems. The problem is an input position may belong to different chunks because, for example, when we copy things wrong or when we do some optimization. And we solve this problem by treating it as a k-set packing problem. Basically, we find the chunks that maximize the coverage. We use a greedy algorithm to do it. Here I will skip the details. If you are interested, actually both of these works are published in papers. So the second component in Tupni is we identify record sequences. The key observation behind this component is an application usually processes a record sequence in a loop. And each iteration of the loop usually processes one single record. And also, a record sequence is usually contiguous in the input. So based on these three observations, our basic idea is we first identify execution loop and the data touched. Then we figure out what data are being touched in each iteration, and they are likely to be the record. So let me use a running example to explain the details. First, we identify in this running example, here's the execution loop. Second, we identify iteration-dependent instructions in each iteration. Iteration-dependent instructions means this instruction touches on different inputs in different iterations. And they are basically, since there are different inputs in different iterations, then they are likely to be the record. Second, after that, based on our observation that all the records are contiguous, then we can find the smallest offsets that are being touched in each iteration. That will tell us the record boundaries. So we just once we figure out the record boundary, we know where the record is because they are contiguous. At the end, we identify termination conditions because the record sequence we want to use it as a constraint. For example, a record sequence, if it's a null terminated string, then the last last byte will be 0. Or it's, may compare with a length field that specifies the size of the record sequence. The third step in Tupni is we identifying record types. The intuition behind it is a record sequence is constructed from a small set of distinct record types, and we want to find these record types. The basic idea is the following: if they have the same record type, then same execution sequence in 2 iterations means the application does the same thing to these 2 records. That means these 2 must have the same record types. One thing I want to point out is this condition is sufficient but not necessary. And however, we didn't observe many problems from this unnecessary condition. Using our running example, here the first record and the third record has the same record type. So in the execution trace, we will see that they trigger the same record handler, so they will see the same execution sequence. And same execution sequence will tell us, oh, they are the same record type because the application does the same thing to them. And of course, there are some exceptions. For example, what if this 2 record data has sub-record sequences or like nested loops? And we handle them by collapse a child loop into a virtual instruction. Basically, if we do a higher level, any loop in the lower level will be collapsed into one instruction when we handle analyze the higher level. Then we go down. So the first step in tuple is we identify constraints. The basic idea is we leverage symbolic predicates. Here's a simple example. As we see this instruction, move the first 2 bytes into AX, add the next 2 bytes onto AX, then compare it with 5. With the dynamic data flow analysis, we can derive a symbolic predicate saying, oh, the first 2 bytes plus the second 2 bytes must equals to 5. And so this gives us a symbolic predicate. And with the symbolic predicates and other techniques, we can infer 4 kinds of constraints, such as length fields that specify the size of a record sequence or the size of a buffer, or a value constraints on single field. For example, saying the type must be 1 or this ID must be 5. Functional constraints on multiple fields, for example, like checksum. The checksum specifies saying the XOR of all the fields in the header must equals to the checksum field. And also intermessage constraints is we track the dependencies between the input message and the output messages. At the end, after we analyze each single input, we will output the format as a BNF rules in a top-down manner. For example, we first start with the root rule at the top level, tells us what the input consists of. Here, in the running example, we see that the first field specify the number of records, then it followed by a record sequence. Here's sequence, and the F1 says the size of a sequence is decided by F1. Then, for each record sequence, we'll have an alternation rule that enumerates all the record types we identify in tuple. Then for each record type, we will enumerate the fields in each record type. And actually, this process will recursively being done because each record type may have a sub-record sequence. We just continue doing it recursively. An important step at the end of tuple is to generalize the formats over multiple inputs. Here, I will show you a simple example. Based on the running example, we may derive 2 formats. They are different. And to merge them together, get a generalized format, we first align all the rules. That means all the top level rule, all the record sequences, and all the record types. For the top rule, we just compare them and put them together. And for record sequences, actually, it's 2 things that I want to say is we have a very easy way to align record sequences because we can use where's the loop, the instruction pointer of where the loop starts. We use that instruction pointer to find to specify the record sequences. Once we find align the 2 record sequences, we just simply merge them as alternation rule. For example, in the first running example, we see 2 types, and then in the second one, we see the third record type, and we just merge them together. Then we continue this process to merge all the record types. So we implement a tuple system, a prototype based on Vigilante and IDNA. IDNA is a tool inside Microsoft that allows people to record this execution sequence. And excluding Vigilante IDNA, we have 14,000 lines of C++ code and 4,000 lines of Perl. We test on tuple on 10 formats, and some of the files, some of the network messages. At the end, we generate a high-quality format for all of them. So I just want to give details on one metric. Here we show that on the 10 formats, we identified all the record sequences based on the second row. We're saying missed sequence is 0. And the third row showing here is wrong sequences. We identify some wrong sequences. The reason is sometimes applications use a loop to process input. However, those input fields are not a record sequence. For instance, there like a JPEG parser use a loop to compare the first some 4 bytes in the input to see if they equal to some specific value. So for this kind of case, we may have wrong sequences. I'll skip this slide. This slide basically tells other experimental results. For example, we have no misclassification error of record types because the condition we use is sufficient. But some records of the same kind may be classified into different types because it's not necessary. So same record type may be treated by processed by different execution sequence, but the inflation is very small. Here's an example to show on the left hand side as a format we can derive from TUCNI. On the right hand side as the documented format we put manually. We can see that we identify all the fields and the constraints with a high accuracy. So I just talked about TUCNI. I ignore some experimental results details. Next, I will tell you about how in Shiogen, how do we generate probes and analyze them. Just go back a little bit. The goal of the Shiogen is to automatically generate a data patch for unknown vulnerabilities given the attack instance and the format. The key idea, if you recall, I said 20 minutes ago, is we want to construct a new attack instance based on the initial attack and the format. And we feed the attack instance to an oracle and decide if that new attack instance will trigger the attack. We can continue that process until we find the vulnerability signature. So for zero-day attack detector, in Shiogen we use a vigilante, and for data analyzer, if the format spec is available, we'll just use GAPA. If the format spec is unavailable, we can use TUCNI to reverse engineer the format of the attack instance. And next, I will focus on this probe generator and analyzer. The basic ideas for probe generator and analyzer is to construct, first we construct this so-called attack-specific initial vulnerabilities predicate. Put another way is we just use the original attack instance as a signature. The problem with that is too specific. Any small changes on that won't be detected by that signature. And then the next step is we generate probes to the zero-day attack detector and to make the predicate vulnerability specific. In other words, is we try to relax the conditions we have in the initial vulnerability predicate. We face two challenges here when we construct the probes. First is how to generate legitimate probes. The second is how to reduce the number of probes. First, I want to ask questions why we only care about legitimate probes. The reason is illegitimate probes should be dropped either by the application or by the input filter. So we don't want to generate invalid probes that will lead us to wrong result. And the key idea about generating legitimate probes is to enforce constraints on various fields based on particle semantics. For example, if you recall, in TUCNI, we want to enforce the constraints on the input, saying, oh, this is a checksum field. Every time when I change the certain fields depending on this checksum, we need to fix the checksum too. And also the length field, like specify the size of the record sequence. So we enforce this constraint so that we'll get a legitimate probes. And the second challenge is to reduce the number of probes. Our key ideas in Shiogen is to first we want to remove all the irrelevant iterative records. Second is we want to eliminate illegitimate probes. And the third one is we focus on the last network message. The reason is that given a message sequence that will trigger the attack, basically most often times the vulnerability sits in the code for handling the last message. And the data analyzer can track the particle context so that we only care about saying the particle state is this and the message look like that. So that will trigger the vulnerability. And so we're only checking the fields in the last message to reduce the number of probes. So that's a basic idea on how we solve these two challenges. in Shieldgen, we do the probe generation in actually in 3 steps. First, we handle buffer overruns because it's a common attack. Second, we remove irrelevant iterative records. And third, we do a sampling on the data fields. So key condition, we want to handle buffer overrun first is because buffer overrun is very common. Second is there's a key condition for buffer overrun is to check the vulnerable buffer size. And how to tell, first we need to solve the problem is how do we tell it's a buffer overrun? We leverage a heuristic. It's basically saying if the offending byte returned by vigilante sits in the middle of a string, then sits in the middle of buffer or byte array, then that's a buffer overrun. Once we find the buffer overrun, we will add a condition in our vulnerability predicate saying the buffer size must be larger than the offset of the offending byte in the string. This tells us the minimal size the buffer overrun attack must have. And secondly is we handle the record sequences. Many popular input formats have iterative records, like the example I showed earlier, like HTML header or this media files. It's a sequence of frames. And the problem is typically only one iterative record in the attack instance matters to the vulnerability. It's only one record. For example, in a WMF attack, it's only one record that will trigger the attack, exploit the vulnerability. All other records doesn't matter. So the problem is if we don't remove iterative records, those irrelevant records, any conditions on these irrelevant records will cause false negatives because those are too specific and unnecessary conditions.
Hello, how are you?
Our advantage here is we can handle iterations because they are specified in a spec, either specified in GAPA spec or they can be inferred by tuple. So we can handle these record sequences. I will use a simple example to explain the basic idea of how we remove irrelevant records. Assuming we have a file input, and the semantic, we parse this file. Say the file has a header and a body. The header has a type, specify the file type and the size, and the body is a iterative record. It's a record sequence, and we parse the body to 3 records, and we continue that we parse each record. And assume that vigilante, the 0-day attack detector, tells us the offending byte is in the second record. Then we'll mark the second record as this offending record. And the first thing we do is we remove all other records in the input. Here, I want to point one thing is we fix the size because the size specifies the file size. After we remove these records, the file size must be adjusted so that we get a valid input. Then we feed this file into the vulnerable program and see if the vulnerable program will be exploited. The 0-day detector, if the vigilante tells us saying, oh, this new file doesn't trigger alarm, then what we do is we add the records back and we remove one record and see if it will still trigger the attack. If it still doesn't, we remove another one, see if it will work. Of course, this is just a basic idea, is see how we can remove irrelevant records. In our actual implementation, we remove the records exponentially so that we don't need to enumerate all the combinations. And the last step in probe generation is to sampling data fields. The goal here is to relax the conditions on the fields left after we remove the irrelevant records. The problem is a combinatorial exhaustive search is not affordable because even a 4-byte field, there are 2 to the 32 possible values. And our target is we want to derive the simple vulnerability conditions. In other words, we want to find the conjunction of conditions on individual fields. We don't look for the combination of on 2 fields, the conditions on 2 fields. And our approach here is to sample data fields independently to to find the don't care fields. The don't care fields is basically saying this field can take any arbitrary value. It doesn't matter. It doesn't matter to the vulnerability. And theoretically, I want to point out is sampling may lead to both false positives and false negatives. For instance, if we miss possible values for attack, then we'll have false negatives. Also, if we're mistaking a field saying it's don't care because we only sample certain values, then we'll have false positives. We'll miss some attack. But in our evaluation, we found that we didn't observe any false positives by doing some sampling. So Shieldgen is we implement a prototype of Shieldgen based on Vigilante, GAPA, and we implement a standalone component to do the probe generation and the vulnerability predicate derivation. And we evaluated Shieldgen based on three metrics. First is accuracy and efficiency and coverage. We do it in two ways. First, we do a case study. We analyze vulnerabilities behind the Slammer, Blaster, and WMF attack. And secondly, we did a vulnerability coverage study to see how many vulnerabilities can be analyzed. Our Shieldgen can derive the vulnerability signature for these vulnerabilities. So for accuracy, as I said, we didn't observe any false positives for the three vulnerabilities. And however, we have false negatives. The reason are mainly twofold. First is we may have an imprecise data spec. If the data spec is not accurate or complete, then we may have false negatives. And second one is we do a sampling. So when we do a sampling, we may have false negatives. For example, WMF have two version numbers. And it's really hard to find the second version number simply by doing sampling. Then we draw a wrong conclusion saying, oh, the version number must be 1.1. Just an example I give. Then we'll miss any WMF exploit that has a different version number. This is a constraint of limited sampling. And but compared with the previous systems, Shieldgen has a far less false negatives than previous system. For example, we can remove iterative records, irrelevant records in WMF. What we find is that you only need one record and one arbitrary record. That's only the two conditions. However, if we don't have a Shieldgen, you can construct an arbitrary WMF file that will exploit the vulnerability. You can have a 10,000 bytes file or like a 1,000 byte file. At the end, we find out you need at least our signature says you have a 112, 118 bytes that will exploit the input. And for RPC, we find out 22 fields are don't care fields, and a previous solution will give a specific condition on that. And for efficiency, we only need to generate a small number of probes since we do a sampling on them. And also, we do for the iteration removal, we do it exponentially. And in our evaluation, we did this vulnerability coverage study. We did a pencil and paper study on 25 out of 157 data patchable vulnerabilities. Basically, in the 3-year frame, Microsoft issued 377 security bulletins. And we went through all the 377 and found that 157 out of them are data patchable, means we can have input filter to filter the attack instances, because rest of them are either access right escalation or cross-site scripting attacks. And for the 157, we randomly pick 25, and in the 25, we found out that 19 of them Shieldgen can generate a data patch. For the six cases, 6 vulnerabilities, we cannot generate data patch. The reason is mainly because they involve complex conditions. For example, if in children we only sample on individual fields. We don't look for the complex conditions such as one field must be greater than the other, or the combined length of two strings must greater than certain size. At the end, we also evaluated the effectiveness of children plus Tupni. So we use a Tupni to reverse engineer the format of a WMF attack instance. Then we use a parsed WMF attack and feed it to the probe generator. And we obtained a high quality vulnerability signature for WMF. Okay, so let me conclude my talk. Today I present the problem is to automatically generate vulnerability signatures for unknown vulnerabilities. And the solution is we want to combine two systems together. One is a children, the other one is Tupni. What Tupni does is Tupni can reverse engineer the input format by identifying fields, record sequences, record types, and constraints, and aggregate them together. And the children will leverage the format of initial attack instances and construct a new attack instance and use a zero-day detector to guide the search to find the vulnerability signature. And we have a working prototype based on Tupni and the children. At the end, we can use a working prototype to generate a high-quality vulnerability signature efficiently. Thank you very much. This is the end of my talk. Please, if you have any questions.
At the beginning of the talk, you said that you only saw 20 vulnerabilities 0 day in like 1 year. What, like, isn't it more efficient, like, for a person to analyze only 20 vulnerabilities?
No, the problem is when you have vulnerability, when you have a zero-day attack, particularly when you have a warm attack, if it takes 4 days or 7 days to do the manual analysis, it could be too late. You want to generate a signature or filter that can be deployed immediately when you observe the zero-day attack. It's not the number of attacks, or it's not the manual analysis can handle that in 3 years. It just takes so long for manual analysis to generate a protection filter when the attack is observed.
Harrison Ford goes into cultures all around the world and tries to find broken stuff and bring it home. That's not what archaeologists do. When archaeologists go to study another society, when they go to excavate the society, they're not usually
Turn your microphone on, please.
interested in what they can find about that culture. And in many cases, things
It's
that
very
tell
easy
about the
to
culture
generate a patch because you have found where the program is run. Is that true? Or?
No, actually, it's from
No.
From my understanding. Generate a software patch is much harder than generate this so-called data patch. Yeah.
What does data patch mean?
Data patch means I give an example here. Is
since you empty the last in the same sense,
I think
just put together
by the way, data patch is a term I think created by Helen Wang. Yeah, and data patch you can think about it's a vulnerability predicate on the input of fields. As here you have a specification of the input, then you create a condition saying if the input look like this, I should drop it. I should throw it out. Yes.
So then, why is it called a patch? Why is it called a data patch?
I think it's just want to draw analogy between data and software. That's why I say that's a term created. Yeah, it's created by Helen. Yeah. Yeah, I mean it's hard. I mean it's different because for data patch you assume you have this spec, and you basically look at the inputs. There are like this is how we do it in children. But for software patch, even you know where is the condition, but I don't think you know the condition. Actually, Bouncer, there's a related work on this. But they also try to generate the input filter. Yeah, for program probably much harder. Maybe Xiang Yu can answer that. How to generate software patch? That seems pretty hard. Yeah.
So I'm curious. So when so you said that when you use GAPA as the specification of format and you use that as the input to ShieldGen, you see some false negative.
Yes.
Did you see similar false negative cases when you have TUBNI combined with ShieldGen? Does TUBNI actually give you wrong specification that lead to the false negative of vulnerability signature?
For that one, actually, our evaluation.
So you
is,
just briefly said that it is good and highly
yes,
accurate.
Yes,
and,
yes.
but-
That one actually, Tupni also give us the similar. I say it's good is because it's comparable with what GAPA can give us, and that false negatives is a limitation in ShieldGen in some sense. Since ShieldGen does sampling on individual fields, and if you, for example, one false negative in WMF is WMF has two versions, and basically one field may take two possible values. If you take either value, it will trigger the attack, or be valid. If you do a sampling, it's really hard to find the second value. And if you don't find the second value, our vulnerability signature will say, oh, this field must take this value, and that will give us a false negative.
If you go to upper class Boston, people speak very differently than if you go to, lower class Dorchester or something like that.
Have you tested this like outside a lab?
Your social experience.
Have you tested this in like real networks?
On real networks, no. What do you mean real networks?
Like, have you ever tried it on a 0 day, like a recent 0 day? I don't know, a recent worm or something that has detected and generated a real signature, or it's just?
Oh, we only test on the three case studies, like a slammer, slammer. Oh, this means so long. Those blaster and the WMF. Yeah. Yeah, but both systems, ShieldGen and the TUPNI, actually currently are taken by antivirus teams inside Microsoft to analyze attack and to generate a signature that can be used by a virus analyst to derive the signature, the input filter.
Organic gardening in California. Those are organic gardens.
No, let's
Thank you.